Good morning to everyone. Am I audible? From students, can anybody reply to me? Am I audible? Thank you. Thank you, Rahul. Thank you, Krishna. Some students are still joining. We will start our session within 1 to 2 minutes. Okay, we will start our session. First, I want to tell you that we started fourth unit in last month itself, and due to the midterm exam, some lectures are lagging for the fourth unit, but still we are in a good position that we covered half fourth unit till now, and next 5 to 6 lectures will be required for the fourth unit, and in that we will see numericals on the fourth unit, that is the isoparametric element. Also, we all three professor, that is Professor Kadpane ma'am, Professor Rakhade sir, and me completed three practicals also. First practical was taken by the Rakhade sir, and it was analysis of truss. Second practical was taken by me, and it was analysis of one-dimensional bar. And third practical covered by the Professor Kadbane ma'am. That was analysis of 1D bar, but including temperature constraint. Okay, so I want to tell you that in last lecture we already covered in last few lectures regarding the fourth unit, we already covered the concept of isoparametric element, aspect ratio, then deviations, why the meshing is necessary, all these concept we covered. And after that, 1 minute, skewness, warp angle, then why it is necessary, isoparametric element, significance of isoparametric element, use of isoparametric element, convergence, compatibility conditions, and to check the validity of isoparametric element, patch test was there. What is the patch test? Then we come to know the coordinate mapping, and for that we required the concept, that is shape functions, natural coordinates, and Cartesian coordinate system. And then we come to know the concept of isoparametric element, subparametric element, and superparametric element. Then to derive the shape functions, we already covered the Lagrangian interpolation, and from that Lagrangian interpolation, we can calculate, or we can derive the equations, and from that equations we already covered, or we already derived the shape functions using the Lagrangian polynomial. And we covered two noded bar element in natural coordinates, in local coordinates, same three noded bar shape functions in a natural coordinates and local coordinates also. Then one element is there, that is a Lagrangian rectangular element. That element is having the four nodes, that is 1 2 3 4. Ultimately, for that element we can use the four shape functions, that is n1, n2, n3, and n4. And shape functions always in Lagrangian, sorry, in isoparametric elements we are going to write in a natural coordinates. So in terms of the zeta and eta, so n1 is 1 minus zeta, n2 is 1 plus zeta, in then next n3 is 1 minus eta upon 2, and n4 is 1 plus it, sorry, so these are the zeta and eta coordinates. And for the Lagrangian element, we come to know the shape functions, that are n1 is equal to 1 minus zeta into 1 minus eta upon 4, n2 is equal to 1 plus zeta into 1 minus eta upon 4, and n3 is equal to 1 plus zeta and 1 plus eta upon 4, and n4 is equal to 1 minus zeta into 1 plus eta upon 4. According to Cartesian coordinate, you can define the zeta and eta sign from this coordinate system. Okay, and this one is the origin, and center of that element, rectangular element, is origin, and unit size of that sides are 2 units. Okay, according to that you can write the shape functions. Okay, and very easy to remember. Then we come to know the another element, that is the higher order element, 9 noded rectangle quadratic element. Okay, so in that we can see here one center node is present in the inner side of the element. Okay, and another element was there, that is the serendipity element, and in that serendipity element there is a no interior node. Okay, so that element is only having the 8 nodes, 4 nodes on the corner, and one node at the center of the edge. Okay, Then we come to know the next part, that is the area coordinates, and I'm going to revise small things regarding the area coordinates. Then we will move to our next today's topic, that is the Jacobian matrix for the CST element, Lagrangian element, and derivation for the Lagrangian element, stiffness matrix. Okay, so area coordinates, I already told you, it's they are itself a shape functions. Okay, and we are using the area coordinates for the simplification. Suppose interpolation functions are there, and you know the coordinates. Okay, then you can write that area a1 upon a is equal to n1, that is the first shape function, and it is equal to zeta. We already know the shape functions for the triangle, that is n1, three shape functions, n1, n2, and n3. Okay, and for the CST element, you already derived the shape functions for the CST element, that is n1 is equal to zeta, n2 is equal to eta, and ultimately n3 is equal to 1 minus zeta minus eta. Okay, so if you are taking the a1 upon a, then what is a1 upon a? A1 is the area of this first triangle. Okay, a2 is area of this second triangle, and a3 is area of this third triangle. Then a1 upon a is equal to zeta, a2 upon a is equal to eta, and a3 upon a is equal to psi is equal to 1 minus zeta minus eta. Ultimately, a1 plus a2 plus a3 upon a is equal to 1. Okay, so area coordinates are equivalent to shape functions in a natural coordinate, and these are also known as the triangular elements. This is the serendipity element. I'm just skipping this because that topic is already covered. Then we will come to know that is Jacobian matrix. And what is the Jacobian matrix, or significance or importance? Any word they can use in a question paper, that is write down the Jacobian significance or importance of the Jacobian matrix. Then Jacobian matrix is required for the transformation form from the natural coordinate system to global coordinate system. Okay, so when you come to the Jacobian matrix, then you have to remember this matrix, that is in the matrix form J. Okay, and this is the 2 by 2 matrix, and in that first row is del x by del zeta and del y by del zeta, and second row is del x by del eta and del y by del eta. Okay, so this Jacobian matrix is required for the transformation from the natural coordinate to the global coordinate. Then we will already derive this Jacobian matrix for the three-noded CST element, and according to isoparametric formulation, if you know the n1 into n3, then suppose this is the triangle, and this interior point 1, sorry, P is having the coordinate system, that is x and y coordinates, and you know the value of x1, y1, x2, y2, and x3, y3. These are the coordinates of nodes 1, 2, and 3. Then you can write x is equal to n1 x1 plus into x2 plus n3 x3, y is equal to n1 y1 plus into y2 plus n3 y3. But we already know that n1 is equal to zeta, n2 is equal to eta, and n3 is equal to 1 minus zeta minus eta. So put the value of n1 into n3, then your equations become x is equal to zeta into x1 plus eta into x2 plus 1 minus zeta minus eta into x3. Similarly for the y coordinates, then I can write these equations rearranging the terms. X is equal to x1 minus x3 into zeta plus x2 minus x3 into eta plus x3. Similarly for the y, y1 minus y3 into zeta plus y2 minus y3 into eta plus y3. Okay, and using notation, I can write here x1 minus x3 as a x13. Similarly, x2 minus x3, it is x23. Don't confuse, that is x13 is equal to x1 minus x3. Okay, so don't take x3 minus x1. It is a silly mistake. Some students already done that type of silly mistake in last academic year. Okay, so y is equal to, similarly, y1 minus y3, it is y13 zeta plus y23 eta plus y3. Okay, it is very simple. So you can write in a matrix form. Our Jacobian matrix is J is equal to del x by del zeta, del y by del zeta, and second row del x by del eta and del y by del eta. But you know the value of del x and del zeta, del x by del zeta, del y by del zeta, del x by del eta, and del y by del eta according to this equation. So take the partial derivative of x with respect to zeta, and you will get that is x13. Next, del y by del zeta, it is y13. Del x by del eta, it is x23, and del y by del eta, it is y23. Now here, what is x13? X13 is equal to x1 minus x3. Y13, y1 minus y3. Okay, so just remember this matrix, and you can derive all these things. Okay. So it is the Jacobian matrix for the CST element if 3 nodes are there. Then Jacobian matrix for the 4 node quadrilateral element, just you have to remember the n1, n2, n3 for the Jacobian matrix, sorry, for the quadrilateral element. Okay, and it is very simple to remember, that is n1, n2, n3 and n4. Then you can write, that is, or you can derive the partial derivative of n1 by zeta. Okay, so it is minus of 1 minus eta upon 4, and similarly take the partial derivative of all shape functions with respect to zeta. So you will get all these 4 value. Okay, with respect to zeta. Then you can take partial derivative of all these shape functions with respect to eta. Then you will get all these 4 terms. Okay, then according to isoparametric formulation for the rectangular element, x is equal to, just pay attention here, n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Okay, and what is the Jacobian matrix? Jacobian matrix is equal to del x by del zeta and del y by del zeta. Okay, so it is the first row. Okay, so for the first row I can write del x by del zeta. So if I want del x by del zeta value, then take the derivative, partial derivative of this equation with respect to zeta. So it comes del n1 by del zeta into x1, del n2 by del zeta into x2. Okay, and that partial differentiation equations you already get from here. So your equations modified here like this. See here, next slide. Del x by del eta, del y by del eta, similarly del x by del zeta and del y by del eta, and put the value of zeta and eta you know in the equations, and you can write the Jacobian matrix. Okay, similar type of example we can see in next few lectures. Okay, next, this topic is new. Just tell me, what is the size of, I want answer from you, what is the size of Jacobian matrix for the CST element? What is the size of the Jacobian matrix for the CST element? It is 2 by 2 or 3 by 3 or 4 by 4. Jacobian size of Jacobian matrix for the CST element. I want answer from Apurva Ratnaparki, Amrut, Umrankar, Aarti Pawar, Abhishek Mate, Aditya Barde, Akash Darvi, Shaha Vedant, Jasmine Sheikh, Miraj Khan, Gaurav Bagul, Gunjan, Nikam, Harshad, Manas, Medha, Nayan, Nilesh, Omkar. Many of you are not attentive for this session. Please pay attention. Piyush, Pooja, Rohan Baviskar, Saurabh Raut, Shubham Nikam, Sunny Chaudhary, Sushant Nikam, Vaibhav Ursal. Yes, I got answer from Prajakta, Bharat, Nikhil and Krishna. It is 2 by 2. Then tell me the answer. If I want to write the Jacobian matrix for the rectangular element, then what will be the size of that Jacobian matrix? Size of Jacobian matrix for the rectangular element. I want answers from you. Jacobian matrix size for the rectangular element. Vijay Rathod, can you give me the answer? Vaibhav, Sunny Chaudhary, Snehal Jadhav, Shubham Nikam, Shubham More, Rohan Baviskar, Pooja Rathod, Piyush, Omkar Rahane, Nayan, Manas, Medha, Rishikesh Lathi, Harshad Raut, Gaurav Bagul, Miraj Khan, Jasmine Sheikh, Akash Darvi, Apurva Ratnaparthi, Aditya Berde, Abhishek Mate, Aarti Pawar. I got some answer from the Aishwarya. Just check the concept or remember the concept for the Jacobian matrix and try to give the right answer. I got answer from the Rahul and Nikhil. Yes, your answer is right. See, whatever may be element, your Jacobian matrix size remains 2 by 2. Okay. So it is not like the stiffness matrix. Your Jacobian matrix is del x by del zeta. Okay, del y by del zeta, and second row del x by del eta, del y by del eta. Okay, so it is always 2 by 2 element, whatever may be, it is always 2 by 2 matrix, whatever it may be rectangular element or CST element or serendipity element or 9 noded rectangular element. Okay, just you have to calculate the x coordinate with respect to zeta, y coordinate derivative for the zeta, and same for the eta. Okay, so it is very simple. Don't confuse between. I got answer from the Nikhil also and Abhishek also. Okay. Aishwarya, are you getting this? Okay, the size of Jacobian matrix is always 2 by 2. Okay, whatever may be element. Next, isoparametric formulation for the quadrilateral. Okay, now see, quadrilateral element is given. Okay, that means you have to consider the 4 noded element. Okay, if it is given that is 9 noded or higher order element or serendipity element, then and then you have to consider 9 noded rectangle or 8 noded rectangular element. Okay, now only quadrilateral element is given, then consider the one rectangular element, center is at the origin. Okay, and 4 nodes are there, 1 2 3 4. The as center is at the origin and the size of this rectangle is the 2 unit, or you can say the square element is the 2 unit. That means from 0 to third number node it is 1 distance. Okay, 1 unit. Okay, so according to that it is -1 for the node 1. For the node 2 it is 1 -1 because x coordinate is in positive quadrant and y coordinate is in negative quadrant. Next, for the third node it is +1. For the fourth node it is -1. Okay, and same rectangular element here expressed in the global coordinate system. It is x1 y1, x2 y2, x3 y3, and x4 y4. Okay, then see here, a square of a side 2 units with a center at the origin is chosen as a master element, and for that x coordinate, x function you can write here like is equal to a1 plus a2 into zeta plus a3 into eta plus a4 into zeta into eta. Now what is this? It is the polynomial function to express the quadrilateral element, and for the y coordinate it is equal to a5 plus a6 into zeta plus a7 into eta plus a8 into zeta into eta, because zeta and eta will remain same for this quadrilateral element, but the constants to define the polynomial equation will be different for the x coordinate and also for the y coordinates. Okay, so very simple to remember, x is equal to a1 plus a2 into zeta plus a3 into eta plus a4 into zeta and eta, and y is equal to a5 plus a6 into zeta plus a7 into eta plus a8 into zeta into eta. Now, but we know the isoparametric formulation, that is for the rectangular element it is equal to x is equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Similarly for the y, n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. Okay, so 1 minute. Okay, to define the displacement or the temperature function, we already know that the shape function is the interpolation function. Okay, so if I know the displacement at node 1, what is that? d1 x1. Displacement at node 2, d2 x2. Sorry, d2x. Displacement at node 3 in a x coordinate, it is d3x, and displacement at node 4 in a x coordinate system, that is d4x4. And shape functions are the interpolation function, and I know the value of n1, n2, n3 and n4. So suppose if I want displacement of point P located inside the element and having the coordinates x and y, then I can write displacement ux, that is displacement in a x direction, is equal to n1 into d1x plus into d2x plus n3 d3x plus n4 d4x. And you can write a symbol like u of x. U of x is equal to n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Then I'm going to consider here u is equal to displacement in a x direction for node 1. u2 is displacement in a x direction for node 2, and u3 is displacement in a x direction for node 3, and u4 is displacement in x direction for node 5. Suppose v of x, that is displacement in a y direction, that is v of y, then my functions will change n1 v1 plus n2 v2 plus n3 v3 plus n4 v4, and instead of u and v, I am using here d1x, d2x, d3x, d4x, that is the displacement of x direction for the node 1, 2, 3 and 4. Similarly, displacement in a y direction, n1 d1y plus n2 d2y plus n3 d3y plus n4 d4y. Okay, because shape function is itself interpolation function. Now, in a matrix form, I can write here ux and uy. This is the 2 row and 1 column element, 1 column matrix is equal to shape function matrix and matrix of u. Now, it is x and y is equal to shape function matrix and x1, y1, x2, y2, x3, y3, x4, y4. If you multiply this shape function matrix with respect to this, then you will get these two equation. Okay. Now, what is the value of n1, n2, n3, n4? Here, n1 is equal to, for the quadrilateral element, how you are going to remember? Center at origin. This is first node, second, third and fourth. Then you have to consider this one is minus 1, minus 1. Here plus 1, minus 1. Here all plus, plus 1, plus 1. And here minus 1, plus 1. So n1 is 1 minus zeta, 1 minus zeta upon 4. n2 is equal to 1 plus zeta, 1 minus zeta upon 4. And n3 is equal to 1 plus zeta into 1 plus zeta upon 4. And n4 is equal to 1 minus zeta into 1 plus zeta upon 4. Okay. So, next, what is the shape function? Shape function matrix is equal to n1 0, n2 0, n3 0, n4 0. Why? Because in a x, for the x, just it is n1, n2, n3, n4, and for that y value is remains 0. Okay, same for the y, x value remains 0 and y value n2, n1, n2, n3 and n4. Okay, so tell me, for this, if you multiply these matrices n matrix into this x1, y1, x2, y2, x3, y3 matrix, then what will be your final matrix size? So this is the 2 by 8 matrix. Okay, and this matrix is having the 8 by 1. Okay, so what is the final matrix size for the x and y? I want answer from you. Bharat, check your answer. Nikhil, Gaurav, Prajakta, you are right. So it is 2 by 1 and itself it will give you the x and y value, 2 by 1 value. Okay, yes, 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 very good, right. Now you are getting my point. Okay, but now this is only for the x and y, and already you know the all four coordinates and the value of the all four coordinates, that is x1 y1 x2 y2 x3 y3 and x4 y4. Okay, then if I want to calculate the stiffness matrix for the isoparametric element, you know the stiffness matrix for the truss element, bar element and even CST element. Okay, now see, you know the relationship that is we already covered in the first lecture, stress strain relationship and strain displacement relationship. This is the strain displacement relationship. Epsilon is equal to B matrix into displacement. This is the strain, this is the displacement. So it is known as the strain displacement relationship, and this is the strain displacement relationship matrix B. Okay, and our second relationship matrix is sigma is equal to D into epsilon, that is it is the stress strain matrix which will give you the stress strain relationship. Okay, and this D matrix is the stress strain relationship matrix, but you can write epsilon is equal to B into D matrix, so sigma is equal to D matrix into B matrix into D matrix. Now why I'm considering here D? Because always you remember that displacement is the primary variable. Okay, see, whatever may be element, if you are going to solve that element in a first lecture itself, I told you that displacement is primary variable. You are always going to solve the numerical for the displacement, that is for the primary variable, and after that you can put here the value of displacement, then you will get the strain, and after that you will get the stress. Okay, so considering the double equation integration, just you have to remember this equation, because if short note will be asked in an exam that write down the short note on the isoparametric element, then you have to write down the stiffness matrix also. So the stiffness, now this one is the elemental stiffness matrix. Okay, just I have to erase all drawing. Elemental stiffness matrix. So suppose if only one element you have to consider, okay, and having the four nodes. Okay, so stiffness matrix for the isoparametric element is equal to triple integration into B transpose matrix into D matrix into B matrix. Now this is the two-dimensional element, so I'm considering here the volume. Okay, in previous units you already solved the numericals on the bar element, truss elements. You did not consider the volume, but you have to consider here the volume because this one is the two-dimensional element. Okay, now what is the value? Volume dV is equal to thickness into dx into dy. You have to consider the thickness value also. So if I'm putting here the value of dV, then your integration, consider the double integration, area to volume is equal to B transpose matrix into D into B matrix, and instead of volume you have to consider here T into dx into dy, where T is the thickness. Okay, now tell me, suppose I'm considering the one element only here. Okay, this one is one element, one rectangular element. Then tell me the size of the stiffness matrix for the first element. Size of the stiffness matrix. How are you going to calculate the size of the stiffness matrix? Element matrix, huh? Not global. Mallar, check your answer. This is not one dimensional. This is two dimensional element. So degree of freedom per node into total number of nodes. This is the formula for the elemental stiffness matrix and itself global stiffness matrix. See, size of the stiffness matrix, degree of freedom, DOF per node, okay, multiply by total, just understand my handwriting. I know that my handwriting is not clear to you, and because I am using the mouse to write, okay. Okay, then tell me, suppose this one is your first element, then tell me the stiffness matrix of size of the stiffness matrix for the first element. I got answer from the Sanket. Let me check. Degree of freedom from node. No, Sanket, your answer is wrong. I want more answer because I want to know where are you going to think about this and at what extent your concepts are clear. I got answer from the Tanmay. Now, first of all, tell me the first answer, degree of freedom per node for this rectangular element. Degree of freedom per node, it is 2, 3, 4 or 1. It is two-dimensional element. Okay, I got answer from the Nikhil, Sanket and Tanmay. Okay, it's very interesting part. Just pay attention here. I got answer from the Rahul, Bharat and Krishna, Gaurav. Okay, you are all you are right. That is degree of freedom per node is 2. Now tell me the total number of node. 4. Okay, so it's not the size of a stiffness matrix. Okay, it is 8 and stiffness matrix is always symmetrical. It is the stiffness matrix property. So your first element matrix size is 8 by 8. Okay, clear to you? Any doubt? Otherwise, I am going to explain another example also. Okay, Nikhil, yes. Are you getting my point? Okay, now tell me, see for the bar element, okay, I'm going to explain it again. Okay, consider this bar element. I'm shifting to the bar element first. Okay, this bar element is having only one element. Okay, next, this bar element having the two nodes and having the one element. Then tell me the stiffness matrix size. Tell me the stiffness matrix size for the bar element. Degree of freedom per node. Degree of freedom per node for the bar element 1. Okay, because it is only one dimensional element. So degree of freedom per node for the bar element is always 1 and total number of nodes is R2. Okay, so it is symmetrical matrix. Stiffness matrix is always symmetrical matrix. So size of the stiffness matrix is 2 by 2. Okay, just forget about this. Now see, suppose second case. Now this bar element is having 3 nodes, 1, 2, 3, and this one is the first element, this one is the second element. Okay, now Bharat, you are saying 3 by 3 matrix. Now what is the size of the elemental stiffness matrix? First, for elemental stiffness matrix, Ajay, don't be in hurry. Okay, I want elemental stiffness matrix size. That is only for the first element or for the second element. So consider only for the first element, degree of freedom per node, it is always 1, and for the first element, how many total number of nodes? So your K1 matrix is having the 2 by 2 matrix and K2 also 2 by 2. But when you are saying the global stiffness matrix size, so I am writing here Kg. Okay, so degree of freedom per node is 1 and how many total number of nodes? 3. So your global stiffness matrix size is having 3 by 3, 3 rows and 3 columns, and you can write that is capital K is equal to K1 plus K2. Okay, and K1 is having size 2 by 2, K2 is having size 2 by 2, but 2 by 2 size for the K1 and the position of the K1 element in the global stiffness matrix is 1 and 2, but for the K2 it is 2 and 3 because node associated with the second element is 2 and 3. Okay, clearly understood this bar element. Okay, and truss element is remaining, but we will see the CST element. Now, CST element, this 1, 2 and 3, and only this CST element, first only one CST element you have to consider. Then tell me the degree of freedom for this CST element. Degree of freedom for this CST element. Okay, I got answer from the Bharat and Sanket. Okay, it's very interesting part. For the CST element, degree of freedom is equal to 2. Okay, and how many nodes? 3. Okay, so here K1 matrix is equal to 6 by 6 matrix. Okay, very simple, and only one element is there, so K1 matrix itself your global stiffness matrix. Okay, okay, Ajay, are you getting this? Nikhil, Rahul, Aishwarya, Sanket, Bharat, Shubham, Abhijit. Okay, okay. Now this is for the CST element, and Rakhade sir will going to take the numerical on the CST element in future lectures. So now I am going to explain you for the quadrilateral element. Now 1, 2, 3, 4. Okay, I know you got the equation for the stiffness matrix. Okay, and you have to solve this stiffness matrix equation. But what will be the size of the stiffness matrix? Suppose this one is only one element. This one is only one rectangular element. Then tell me size. Size of K1 matrix. Degree of freedom per node for this rectangular element 2. Okay, total number of nodes 4. Okay, so K1 is equal to 8 by 8 matrix. Okay, clearly understood? Okay, now your second case. This one is the rectangular element. 1, 2, 3, 4, 5, 6. But two parts are there. Two rectangular element is there for total one structure. Okay, then tell me the size of first element. Tell me the size of the stiffness matrix for the first element. How many degree of freedom? 2. Okay, and total number of nodes 4. So K1 is 8 by 8 matrix. Okay, next K2 is also 8 by 8 matrix. Okay, now tell me the size of the global stiffness matrix, that is capital K global. So I am writing here G. How many degree of freedom? 2. Now don't confuse. How many total number of nodes? 1, 2, 3, 4, 5, 6. Total number of nodes are 6. Okay, so 12 by 12 matrix. It's 12 by 12 matrix. Now in this 12 by 12 matrix, what is the position of this K1 matrix? What will be the position of the K1 matrix? Okay, don't confuse. Okay, I'm going to explain it for the truss problem. Then you will get to know what is the position of the K1 matrix and K2 matrix in a global stiffness matrix. Now, till here, concept is clear. Are you getting this? Global stiffness matrix size is 12 by 12. Okay, I got the answer from the Nikhil and Ajay. Just write down yes if you are getting this. Are you getting this? Is it clear to you? Yes or no? Just I want answer from you. Okay, 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 okay. Now, it is okay that the size of stiffness matrix, it is equal to degree of freedom into the total number of nodes. And you know the equation also for the stiffness matrix for the isoparametric element, and you have to solve this equation. Now, is it easy to solve every time this type of double integration which includes the matrix? Is it easy to solve this type of double integration if uh, this type of matrices are involved? No. Then how are you going to solve this type of matrix? How are you going to solve this matrix? In numerical integration, in NMO, you already covered that numerical integration. Okay, so can I solve this equation with the help of the numerical integration, Gauss 2-point and 3-point formula? Yes or no? Yes, and it is very simple. Just you have to put down the value. Okay, so your next part is Gauss 2-point and 3-point formula that is applicable for the solving of the this type of equation. Okay, but one concept is remaining. Okay, one concept. Which concept is remaining? We will see. Okay, see, this is dx and dy. Is this natural coordinate or local coordinate? Dx and dy. Is this natural coordinate or global or local coordinates? Natural or local? Just tell me your answer. Local coordinates. Okay. But if I want to convert this local coordinates into natural coordinates, because I know the value of shape functions and shape functions itself is explained in a zeta and eta coordinates. So I want to transfer from this natural coordinate system to the local coordinate system to the natural coordinate system. Then what I supposed to do? Okay, I got answer from the Nikhil and Aishwarya that it is a local coordinate. Okay, and I want to convert this equation from local coordinate system to the natural coordinate system. Then what I supposed to do? Jacobian matrix. Okay, I am using here Jacobian matrix for the transformation from one coordinate system to the another coordinate system. Okay, so dx and dy in a natural coordinate system, you can write it is equal to determinant of j into d zeta into d eta, where d zeta and d eta is the natural coordinates, and your modified equation it is now. See here, integral limits also change here from -1 to 1 because you are using the natural coordinates, and natural coordinates magnitude lies between the -1 to 1. So for the double integration -1 to 1, okay, for the zeta and eta, and in the integration form it is a B transpose matrix, B matrix thickness determinant of J into d zeta into d eta. Okay, very simple to remember. Just you have to remind these things because derivation is not asked, and if you want where it comes from this equation, then you can refer the reference book, that is finite element analysis from the Chandru Patla. Okay, Chandru Patla is the author name. Okay, so this is all about the isoparametric element and stiffness matrix, and here thickness is included because this is the two-dimensional element, and we already covered the uniqueness mapping of the isoparametric element in the last lecture. Yes, I know, Ajay, you have to learn because derivation is not asked in your finite element syllabus, in your B syllabus. It is required that just get the concept. Okay, these are the learning outcomes that you should know the concept regarding the finite element analysis regarding the one dimensional element, two dimensional element, isoparametric element, temperature, and some basic part of the vibrational analysis, that is the modal analysis. Okay, and it is very interesting unit also. Just it is learning outcome that just clear the concept. Okay, so we will move ahead. Uniqueness of mapping. I already told you, suppose this one is total perfect square element. Okay, and I want to convert this element into the isoparametric element like this. But while conversion, there are a distortion. See, this one, and this one. Okay, so when there is a distortion, then there is a negative value of Jacobian matrix. So if we are solve that type of Jacobian matrix for this type of element, then the value of Jacobian matrix will be negative. And if Jacobian matrix is negative, then your computer program will automatically terminate it. Okay, it will give you the error because there is a distortion. You are putting the input to the computer that it is the isoparametric element, this is having the 4 nodes or 8 node or 9 node, but they can recognize that Jacobian matrix is negative, so there is a distortion. That program or that computer will give you the error. Then you need to know that there is a violation of the rule, there is a not perfect element is manufactured. Okay, so you have to again check the mapping, you have to check the again element to avoid this type of distortion. And suppose distortion comes, that Jacobian matrix will gives you the negative value, program will terminate it, and then you have to solve that distortion shape and you have to correct that shape. And there is a procedure in a software also that you can modify the meshing elements also. Okay, so it is clear to you, that is mapping of the isoparametric elements. Okay, then there are three theorems. Isoparametric concept is developed based on the following three theorems. I don't know, even you don't know what will be your in same paper pattern. Is it multiple choice or is it a descriptive type? But suppose descriptive type is there, and then you have to write down all this theorem if the question asks. Okay, and there are favorite questions from the university that write down the theorems of the isoparametric, write down the no short note on the isoparametric element, write down the short note on the natural and local coordinates, or write down the rules of the shape functions, or qualities of the shape functions, write down the C0, C1, C2 continuity. That is I'm going to explain in the next lecture. Okay, but first of all we will see the theorem. First theorem, if two adjacent elements are generated using the shape function, then there is a continuity at a common edge. See, isoparametric element you have to derive from your simple element. Okay, this one is your simple element and you have to derive the isoparametric element that are having the curved side and your angle is not restricted to 90 degree. And suppose these two adjacent elements are generated using the shape function, then there is a continuity at the common edge. Okay, second theorem, it states if the shape functions used are such that continuity of displacement is represent in the parent element, and this one is the parent element, then continuity requirement will be satisfied in the child element, that one is the isoparametric element. Next, third theorem, the constant derivative condition and condition for the rigid body are satisfied for the isoparametric element if summation of the shape function is equal to 1. So there is a important rule for the shape function also, that n1 plus n2 plus n3 plus n4 is equal to 1. So points to remember, that there should be continuity at a common edge. This one is the point to remember from the first theorem. Second, suppose continuity at a displacement in the parent element, then that condition is also satisfied by the child element, that is the isoparametric element. And third theorem, constant derivative condition and rigid body displacement condition that we already covered in the convergence criteria is satisfied only if summation of the shape function is equal to 1. Okay, so it is very simple if you remember the key points from the all theorems. Okay, now we will stop here. If you have any doubt regarding the today's topic, then you can put in a question box. Otherwise, we will end this session. So I will wait for the 2 to 3 minutes. Then write down your in if you have any doubt. And also one notice is there from the tomorrow's lecture, please bring your calculator and please keep pen and paper with you, because from next lecture we are going to solve the numericals. We don't know, Sanket, university will going to send all details. We don't know. Really, we don't know where, when and where and what is the format of the INSEM exam. But when university will send the details, then we will let you know. And I don't think that university will give you details within 1 to 2 weeks, because university is busy now for the final year exam, in the final year exam. Okay, so if you have any doubt regarding today's topic, tell me. Otherwise, you can leave the session. I will wait for the 2 to 3 minutes more. If you have any doubt, write down in a question box. Okay, thank you for the joining this lecture. Thank you for listening. I'm going to end this webinar.